Well, greetings and welcome to Nani Notes. Here we are in, oh gosh, the 110. We're still in Unit 1, but it looks like it looks like we should be in a new chapter. This is kind of looks like a new unit, but let's have a look here. Rigid transformations. As illustrated here, we're showing a composite. I'm going to slide or make a vector translation there, and then I'm going to reflect this image across this axis of symmetry, and I get a resulting image. Wow. Yeah. Okay, well, you're going to have some notes to take, so get those pencils sharpened, and let's get to it. Oof. Oh, first off, this page, kind of the warm-up page, page 69. And I think we're going to go up to about 74 on this video. We're going to save the exercises for another video. We got enough to do here. Yeah, what do you notice? What do you wonder? You're given this very interesting grid, this very interesting graph paper, and you're given these pretty colors and all these points. And well, do you notice anything? Yeah, I know you do. You're probably noticing the graph itself, the graph paper itself. Well, if you're in my class, yeah, you probably say, oh, I recognize that now. I know that is isometric graph. And we know what it's for. In reality, it just looks like a bunch of hexagons or equilateral triangles. But just keep staring at it. Just stare at it. Really, really stare at it. And what do you see? You're going to probably see three-dimensional shapes. You just imagine. I mean, this is a just a regular hexagon, but the way we shaded it makes it look like a cube. All right, well, we'll just show a few pictures at the end, remind you what we did in class. But really, right now, we're just looking at this as regular graph paper. So let's get this isometric out of there. What is going on here? Well, I've got this blue and this green. Well, the green's bigger than the blue, but it looks to have the same shape. And as a matter of fact, well, I guess we don't have any theorems for this yet, but we can demonstrate that this green is similar. Well, okay, let's do something better. They gave you this O here for a reason. So let's focus on the relationship between the blue and the green. I'm sure you all noticed. Let me grab my, where's my ray? There we go. That if I were to start from here, all of these are collinear, right? In the same way, if I start from O, go through A and E, they all line up. Well, that's no coincidence. I'm going to go from here through B and through F. And what you are demonstrating right there, what you are demonstrating is that D is in fact an enlargement of S. Now we have a word for that. It's called a dilation. Now I noticed they use different notation, A, B, C, D, E, F, G, H. Well, the question you might ask is that a transformation? Well, yeah, it is. A dilation is a transformation. However, it is not a rigid transformation. It does not preserve the shape. Just by its very nature, a dilation makes an object bigger or smaller, or however, it keeps it similar, meaning it is the same. Well, it's just shrunk or enlarged. All right, let's clear that out of there. And actually, let's see if we can get rid of that. I'm going to leave the dots there so you know where it was. Let's look at the relationship between these guys. And you're probably noticing the A prime, B prime. And that's the kind of talk we use in a translation or in a transformation. When A is transformed by some means, it goes over to a place called, well, it becomes A prime. B maps onto B prime, C to C prime, etc. And if I look at this, Watch this. I'm going to connect. You can go ahead and do this with on your paper. And you're saying A to A prime. There seems to be a relationship there. And if you took your compass, you could actually demonstrate that to be very true. A to A prime back to A. And look at that. You've constructed the perpendicular bisector. And what do you know? M, which is or in this case, it's going to be the axis of reflection. M is the perpendicular bisector. That's really cool. And if you really went nuts on this, you would demonstrate that that's going to be true for all the points. Let's just check to see here. Go to Charlie prime, and exactly the same thing. So if I were to take my compass and swing it back again, you're going to see that M is the perpendicular bisector of C prime. The same would be true for D and D prime. That's our observation about what a reflection looks like. Let's clean this up a little bit. Now, if I just looked at these segments, if I'm tracking from C to C prime, you could see I'm going through this diagonally, 1, 2, 1, 2 on the other side. The relationship, there's actually a relationship, which is to say that in a reflection, this distance, this is the midpoint between the two, and there's a right angle formed, and hence the perpendicular bisector. Wow. So if I go from C, perpendicular to the axis of reflection, then I'm just going to go that same distance on the other side. Hey, that's kind of cool. But we're just making observations now. And that's on 69. We're going to turn to 70 and say, can you take that and do something with it? All right, let's do it. Yikes. Now, this confused me a little bit because they've got a vector V down here. I guess they called it something else. They said path. But that's the path. A vector is it means that I've got a magnitude and a direction, or as you say, a path. Now, they've got this one vector here, and we're going to start by translating this figure along the vector, and we're going to label it T. So we're going to do this slowly, and maybe I'll put the big dots out so you can see them. If I take this dot by that vector, it's going there, 1, 2, in this direction. Take this corner, 1, 2. Take this edge right here, 1, 2. Take this one, 1, 2. We can go all the way around the figure like this, 1, 2. This corner, 1, 2. And now all we got to do is just connect them. Now, if I ask Sketchpad to do that, it would shade it in really nicely, and it would actually call it a hexagon, because the truth is, this is a hexagon. I count the sides, 1, 2, 3, 4, 5, 6. What do you know? Now, it's a little funky because it is not a regular, it's not even concave, or it's not even convex, that is a concave hexagon. So there, I'm going to shade it in like that. Connect the points and shade them in. That's we call it a preimage. That's the preimage S, and we're going to shift it along that vector V. So we shifted it over 2 units. Easy squeezy. So now a little bit more challenging. We're going to reflect it across the Y. Now the computer could do that easy, but we're going to do it even more fun. We're going like this. Now, again, I'm going to go point by point. Look at this point. Look at this. All right, so we're going, so what did I do there? It's like kind of 1/2 of these junctions, a half, 1. This point is going to map over to here. I'm going to take this point Right there. Do you see it? You will with practice. Look at this one. Think of it as you're traversing two of these diamonds. 1, 2, 1, 2. Now down here. 1, 2, 1, 2. Oh, it's coming together. How about here? 1, 2 and a half, 1, 2. And this point up here, S, 1, 2 and a half, 1. Wow. Connect those dots. Now this is a little funky. I'm just doing this. I go 1, 2, 3, 4, 5, 6. Watch what happens. I pull down the construct menu. Oops, I have something else selected. Dang it. 1, 2, 3, 4, 5, 6. Construct. Look what it says right there. That's a why? Because it's a hexagon. That's the hexagon interior. And we're going to call that, they left a blank. I'm not sure what they meant. They meaning the authors of this, but since they started by naming this figure an S, a capital S, meaning they're naming that for the entire figure. I'm just picking some random letters. F for flip, because we flipped it over the y-axis. How's that for fun? Ooh, oh yeah, ooh, this is going to be a tough one. We are now going to reflect figure S across M. This one, I practiced this one. This one's a little trickier. Yeah, actually it's a lot trickier. And we're going to go point by point. So again, you're reflecting across this line. Now ignore this little green W vector here because we're not doing that. That's last. So again, point by point. Going across the diamond, I'm going to come across to here. So these 2 points line up. This one to here to here. We're going point by point. Coming up here. 1 and a half, 1. Now you'll figure your own way of counting this, but just look at it. You're going here, I'm traversing across that diamond, and a half, and that other diamond. You gotta go one at a time, because otherwise you can get really, really confused. I actually got confused right there. I thought I was looking at this purple T. I forgot where I was. Okay, now I'm up on this point. 1, 2, 1, 2. Whew. And now this point. 1, 2, 1, 2. Now connect those. 1, 2, 3, 4, 5, 6. Connect those very carefully and see what you've got. Now, in our earlier talk of isometric, it looks like the same shape in different planes or something, but yeah, we're just having some fun with this. Now the last one, on 4, it says translate figure S. Notice they keep going back to the figure S. This is not composite. We'll talk about that in the next page. And we're going to translate it along the vector W. Now the vector W is down here, but it doesn't mean it actually goes there. I mean, it just means that, that's the path. And well, this is my interpretation. You're just going 5 units. 1, 2, 3, 4, 5. That's what this vector shows me. It's a magnitude and a direction. So I'm going to go back to this guy. And I'm going to say 1, 2, 3, 4, 5. And again, I'm following this along this axis now. 1, 2, 3, 4, 5. Up here, 1, 2, 3, 4, 5. here. 1, 2, 4, 5. Up here. 1, 2, 4, 5. Okay, we're just about done. And this corner. 1, 2, 4, 5. And you can see it taking shape right there, right before your eyes. And I'm just going to call that one H. How are they similar? You know, how are they different? I mean, look at this. This one, you've got two that have been reflected, and you've got two that have just been slid over. It almost looks like you just took it and you turned it. You know, imagine that. Imagine that, like our example with when we were using that hexagon to make it look like a box. Look at that. Well, just think about that for a little while and admire it, because that was fun and that was a little bit of work, right? Okay, it's showtime. Let's go to the next one. Oh, yay. You know, this is interesting. You know, we're defining congruence, and I'm glad to see a definition coming up. That congruence means that I can take an object and through a series of rigid, mind you, rigid transformations, I can map it onto another object. Then they are congruent. I like that. So I want you to imagine on this one right here, I'm going to take A. So this is number 1. I'm going to take A, and it's going to take me 2 moves to get it to B. I could slide it over 1 there, right? And I could flip it down like that. Now, if I did that, that was, again, 2 moves to go from A to B. And now you're thinking, well, what if I reversed the order? Does A still end up on top of B? So back this up a little bit. Reverse the order means I'm going to flip it first and then slide it. So we did 1. 1 was slide, 2 to the left, flip over the red line. Now we're going to try this. Oops, I'm getting ahead of myself. I'm going to take this. I'll let the computer do it this time. And I'm going to reflect it. Transform. Reflect. So you can see this preimage, or this object A, reflected first ends up here. And it doesn't take a lot of imagination to see that if I take this object and slide it 2 units to the left, it's going to map exactly on top of B. So this slide to the left, flip, has the exact same outcome as flip and slide to the left. The order did not matter in that case. But now I'm going to try a different one. How are we going to get from A to C? Well, there's a couple ways we can do it. I'm going to take a line here, take an axis, and I'm going to say, well, okay, if I were to reflect across this line, so I'm going to take A, and I can reflect it across this 45-degree line. And if you don't believe, like you could have found this yourself. I mean, we're gonna, you know, and it does take a little bit of work. See, if I draw that, yeah, that looks like. If I draw this, that may help you visualize it. Every one of these, this line is my perpendicular bisector. So if I flipped it across that line, and I want you to find that line, go ahead and draw these other segments in just to prove it to yourself. Do it so you can see it. That reflection gets my figure over here. And then clearly I've got to slide 2 units to the right. So a reflection and a well, either a glide transformation or what they sometimes call a vector translation. Flip and glide, flip and glide. Let's switch the order. Let's see what happens then. Now, if I slide this over 2 units first, watch what happens when I flip it. Ruh-roh. It does not end up in the same place. It does not end up on top of this figure. So these two were not reversible. 1 and 2 mapped A onto B in either order, but 3 and 4 don't. There's something different about them. And we're going to just experience that, and we'll come up with some ideas about that. But I just want you to be able to draw that for now. All right. And then comes the fun stuff. Now, I'm going to show you some things, but I want you to make up your own. I'm having a little fun with this. And this is composite transformations, which we were just talking about. Does the order matter? Now, when I was first teaching, my students were using Geometry Sketchpad, we would draw something like this, like a letter, because it really shows up well how it transforms, if it's reflecting, if it's rotating, rather than some symmetric figure. So I picked this letter J, my first initial, and I'm going to take it like this. I'm going to go through a couple different composites. I'm going to do a vector. I'm going to slide it this direction, the red, then the green. Ready? Now, you can see that this is defining the vector come on. This is defining the vector translation. I'm saying go this way. And this defines the second translation. And you can even see this is what happens. That's a composite transformation. But watch this. We are going to switch it up. We're going to say, let's do the green first. I'm going back to here. Let's do this first and then do this. Now this one will show up. This will make sense to you. All right? Now watch what we got. It's amazing. So I'm going to do this first, then this, and it doesn't matter. I still end up right there. Absolutely amazing. And it's fun. It's fun. But hang on to your hats, because this might be different. We're going to reflect and then rotate. So, I think I set it up this way. Okay, that's reflection first. And you see I could move the axis of reflection. That's going to change where my image is. And now I'm going to take that and I'm going to rotate it. This is my angle of rotation. That's 0. That's about 90. Look at that. And that's about 180. So I'm going to put it down for 90. Now pay careful attention to this, because we're going to try to reverse the order and see what we've got here. I'm going to first rotate the original J. This one takes a little bit of focus to watch, right? So again, I'm rotating the original J over here. Now watch what happens when I reflect that one. Uh-oh. Now I got three J's stacked on top of each other, but if you look carefully, you should be able to see. Check it out. This is the one right here. That's the one that was reflected and rotated 90 degrees. This is the one that was rotated 90 degrees, then reflected. It's going another direction. This one does not work. Well, it doesn't work, meaning if I switch the order, I do not get to the same place. Really cool. Okay, next one. You know, I had so much fun with this. I made a couple more. I just wanted you to see them. All right, this looks like the same thing. Oh, no, it isn't. I guess it isn't. So I'm going to do this. I'm going to take a vector, and then I'm going to rotate it. Okay, and now also, at what point are you rotating? You know, I could have probably made it neater by rotating by some exterior point, but I'm rotating by this point in the middle of the J. All right, now let's switch the order. No, that's not it. No, that's not it. I'm losing track of all my little buttons. All right, hang on. Well, that doesn't really show me what I wanted to show. All right. No, that's it. No, that's it. Ah, here we go. So there's the rotation first, and then here is the translation. And of course, you can't see it because it ends up in exactly the same place. So if I'm going to take my J and slide it over and then rotate it, I get this exact same thing as if I rotate it first and slide that rotation over on that vector. These two are reversible. Wow. There's a lot to this, isn't there? Let's clean it up and do something else. One more. No, did we already? No, we already did that. How about these two operations? Oh yeah, vector and axis of reflection. And I think you'll probably come up with something right away. You're going to start to come up with an idea. So clearly, when I say a vector, from J, I'm sliding J over like that. That's the path that I'm sliding J. And then I flip it across this axis of reflection. So again, slide the J, then reflect it. Now, if I were to do this though, if I were to go back to the original and reflect it, it's going to end up way over here. Why? Because remember, at any one of these points, if I were to connect this point to its corresponding point, it'd be way down here. And yeah, that's the perpendicular bisector, that axis of reflection. It ends up way over there. In the same way, that the axis of reflection splits that segment in half. That's how the mirror works. Now, this is taking the blue and reflecting it first, but look at the vector. The vector's over there. So when I do that, yeah, it even goes off the page. I'm going to change this up a little bit so I don't go losing my vector. But look at that. I end up, after slide and reflect, I end up here. After reflect, then slide, I end up way over there. Not the same. Wow. Okay, well, I hope you got some familiarity with this. There's some ideas that are coming out here. Oh my gosh. The image is the result. When I perform an operation on what we usually call the pre-image, then the result is the image. An assertion, I don't use that word a lot, but I guess we may use it in common language. I believe this is true. And look, congruent. Finally, we've got something about congruent. If there's a sequence of translations, rotations, reflections that take the first onto the second. So we should say congruence transfer, rigid transformations. I like that. And theorem. That is a statement that's been proven. Now you already know, well, heck, you've all heard of the Pythagorean theorem, but there are so many other theorems. And hopefully we'll be doing some proofs as this class progresses. So, I think we're going to wind it down there. And I'm just going to say we had a lot of fun with, with our various shapes. Look at all that. That was a lot. And I just want to end with this thought. Remember, we did this for, well, those of you in my class, if you drew this, yeah, that's what you usually see isometric paper used for, making 3D models or something, or converting a 3-view orthogonal into a 3D looking drawing. And that was fun. So I'm glad you all got to enjoy that. And I'd say that's it for now. It'll be a separate video for the exercises. See if you can tackle those on your own. If you can't, come back and check with Nani Notes. And as always, thank you for watching.